Alright guys, this video is going to cover what's known as Ohm's law and the series circuit. It's going to have three very important terms: current, voltage, and resistance, and those are going to be used over and over and over again. So this might be the most important video out of the set for the week. So let's just start with a basic circuit. So what do you need to make a circuit? Well, you need a power source. That's going to be our battery. We already talked about the role of that. We're going to need a closed conducting loop. So it has to be wires. It can't be yarn, right? It has to be a conductor, which allows the flow of electrons. And then I also have to have a load. Now, a load is what is known as a circuit element. And basically, it's just anything that's connected in the circuit. You have to have those three things to have a circuit: a power supply, a closed conducting path or loop, and then some sort of load. A common term is that if you don't have a load in the circuit, and this is just a wire that connects one side of the battery to the other, this is called a short circuit. So a short circuit is one that is not functional for the purposes of doing anything but creating a whole lot of heat. So basically, if you think about it, there's nothing to use up the energy of the electrons running through the wires, and so they'll just get faster and faster and faster, and eventually they can cause a meltdown of the wires or even the battery to catch fire. So that's one of the questions on the practice homework for today is, what is a short circuit? And that is a circuit in which there is no load, but there is a power source and there is a closed conducting loop. So those are the things we need for a circuit. Now, Ohm's law, on a very basic note, is the law that describes how these three things act in a circuit. Now, we first have to define what they are, so then we can see how they relate to each other. Now, the little simulator you're going to use today in class after watching this video is going to allow you to gain the relationships to help build the equation. Alright, so the first term, and maybe one of the more important terms, is voltage. I guess they're all equally important. But let's take a look at voltage. Now, voltage actually means, or is analogous to saying, or describing, a potential difference. So voltage is not actually like fluid, like a mass, or a measurement of amount of substance. It's a measure of the potential difference between two locations. So here's what we mean. If you take a battery, let's say that this is a 6-volt battery, so that would be the units of voltage, by the way, is the volt. Alright, a 6-volt battery, all that says is, okay, we know this already, that this is called the place of high potential. This is called the place of low potential. So the difference in the potential from the one end to the other is 6 volts. So instead of saying, what we could say is, what is the potential difference of the battery, which is a 6-volt potential difference. In other words, if this potential is 6, this side is 0. Or you could even do something like, this is 3 and this is -3. But for our purposes, we're always going to say that it's 0 and whatever the voltage is. So you can say either, what is the potential difference across the battery, that's the terminology used, or you can say, what is the voltage of the battery? And the thing is, you can figure out the potential difference between any two places in a circuit. So, in other words, if you had a wire connecting this, once again with our example of the light bulb, what I could say is, what's the potential difference between this point A and this point B? Or, what's the potential difference between this point B and this point C? So we're going to talk about that as we go through this video, but it's really important to understand that voltage is not a quantity of substance. It's not like the amount of juice in the battery. It's actually describing what is the difference between the sides of the battery. In other words, basically, how many joules of energy per electron charge that the battery can do in terms of work. So in this case, that means it could do 6 joules of work for every coulomb of charge. So for every charge of an electron, I can do X amount of energy in the form of work. So that's what voltage refers to. Let's take a look at what current refers to. Alright, so current is not speed of electrons, that's important. So let's assume that we have a wire here, and we're just zoomed in on a piece of wire. So let's pretend that it is connected to a battery. I guess I can go ahead and just show that. Okay, so there is current running through this wire. Now if we took a point in the wire like this, and we counted the number of charges that pass that point in a given amount of time, we would actually be describing the current in that circuit. So an analogy would be, you stand on the side of Inwood Road, looking at it from above. You stand over here, and you count the number of cars that pass the point where you're standing in, let's say, an hour. So you use a little clicker, you count how many cars pass in an hour, and basically what you can report to whoever asks is how many cars pass through that part of Inwood Road in a second, in an hour, in any amount of time that you convert it to. So that's what current is describing. It's describing the amount of charge passing a point in a certain amount of time. So we know that charge is measured in coulombs and time is measured in seconds. So a coulomb per second is equal to what we call an ampere, which we usually shorten with amp, which uses the uppercase A. Now in physics, current is represented with the letter I, so that's the symbol for current. But the units of current is the amp. So just like mass uses the symbol M, but the units of mass are kilograms, kgs, this is an analogous situation. Okay, so current is the amount of charge, which you could also look at as the number of charges, that pass a point in a certain amount of time. Alright, let's look at resistance. So resistance, just like it may sound, well, I can't spell that. Alright, so resistance is going to be a hindrance to the flow of charge. Now, we have things in circuits that we call resistors specifically, and their job is purely just to hinder the charge. So a resistor oftentimes looks like this little thing. It has wire, there's this little kind of plasticky looking thing with colored bands on it, and another wire that comes out the other side. And its whole job is to resist the current, so to slow down the current. Alright, so resistance hinders the flow of charge. It's measured in ohms, and we use the symbol omega for ohms. So if this was a 200 ohm resistor, I would write that this 200 ohms resistance is the value of that resistor. So the symbol for resistance is R, but the symbol for the units is the ohm, which is that Greek letter omega. Now, pretty much anything in a circuit that we described before as the load of the circuit, anything in a circuit, the circuit element, is a resistance. Technically, even the wires are a resistance, but most of the time we assume that that resistance is negligible, so we basically ignore the resistance of the wires. But anything that's using up the electric potential energy of the charges that are moving through the wires is considered to have resistance. So let's look at how these things relate to each other. At this point, what you should do is pause the video and complete the activity that is listed in the simulation. Then when you're done with that, come back to this video and continue watching. Alright, so hopefully you did pause the video and actually do the assignment. And what you should have seen is, you might have struggled at first to figure out how the heck do you measure the current. And it referred to an ammeter, okay, in the instructions. And basically an ammeter just measures current. So what you probably saw was that you had to have a continuous loop, you had to have a battery, you had to have an ammeter, I'm going to make that the symbol with A, and then you had a resistor, which I'll use an R, that connects to the battery, which we'll call B. And you should have had something that looks like this. Now this kind of circuit is what we call a series circuit. And what all that means is that each circuit element, in other words, all the things that are in the circuit, in this case the ammeter, the resistor, the battery, all three of those things are connected one right after another. So there is no other place for the current to go. So in terms of the battery, the current's going to flow through these wires, through the resistor, through the ammeter, and back to the other side of the battery. And it's always going to flow from the high potential side to the low potential side. And this is natural on what we call the external circuit. Inside the battery, that's where the unnatural stuff is happening, where the chemical energy is pushing up electrons. So what we say is that an ammeter has to be connected in series if you want to measure the current. Now this is opposed to what we call connecting something in parallel. So I'm going to scoot to a new slide to show you what I mean. Alright, I might have a battery, a resistor, and an ammeter, and this is, all three of those things are connected in series. Now, the other term, what we call parallel, is when you connect something in its own little branch. So here's what I mean. Okay, here we have a battery, we have a resistor again. We know that the current has to flow through the ammeter in order for us to know what the current is. But what if I wanted to measure the potential difference, if you remember that from earlier on in the video, between this side of the resistor and this side of the resistor? Well, there I'm going to use what we call the voltmeter. And the voltmeter is connected in parallel. So you can see there that if current was flowing through this circuit, it would get to this point and it could either go through the voltmeter and keep going, or it would go through the resistor. Now the trick of a voltmeter is that you don't want the current to escape and go through the voltmeter. So in actuality, what's going to happen is this is going to prevent current from going through it, but at the same time it's still going to be measuring the voltage across the resistor. So let's talk about why you would even want to measure that. Well, if you have a battery that says 6 volts, as the current passes through the wire here, it hits this resistor. There is what we call a voltage drop as we go through this resistor. Now, a voltage drop is basically describing that some of the electric potential energy of the charge is being used up. So the charge is not being used up, but the electric potential energy that it carries is being used up. An example of this would be if you had, if you were a car going through a toll booth where you still had to pay. So when you go through the toll booth, which is analogous to the resistor, you don't pay with your car, so you don't get used up as you go through it. So that your car is like the little charge. Now the charge is carrying energy, you're